So Curie was focused on finding different radioactive elements. Ernest Rutherford and others were looking at characterizing radioactivity itself. So this new field is opening up, and there are lots of different aspects to be studied. And this Rutherford is the same one who did the other experiments we learned about in 1A. So the nuclei of these radioactive elements are unstable, and they just fall apart, basically. They spontaneously decompose, and it's not like they crumble, but they spit out little tiny pieces, and in doing that, they become more stable. So there are different categories of natural radioactivity: alpha decay, beta decay, gamma ray emission, positron emission, and electron capture. And we'll briefly talk about all of those. The first three are named from the first three letters of the Greek alphabet. So this is alpha, beta, and gamma. So just a review of nuclear symbols. We covered this in 1A, but maybe you don't remember all the details. So we can symbolize an isotope in this way, where the big X is the chemical symbol, that's the element symbol on the periodic table. On the left as a subscript is the atomic number, that's the number of protons in the nucleus. And then the mass number is a superscript on the left. The mass number is the total number of protons and neutrons in the nucleus. So it's the number of massive particles. And the mass number will be very similar to the actual atomic mass in atomic mass units of that atom. Atomic number is the number of protons. And so if we want to know the number of neutrons, we just take the mass number and subtract the atomic number. And this is kind of nicely, oh, my pencil's dead. Nice. You could set this up for subtraction. A minus Z gives you N. So that's handy. Most elements have several different isotopes. Some only have one, but most of them have 2 or 3 or 4, and you don't get that information on the periodic table. So we often refer to a specific isotope of an element as a nuclide. We can represent isotopes using those nuclear symbols. We can also represent them using either the element name or the symbol followed by the mass number. So something like carbon-14 or C13 would represent 2 specific isotopes of carbon. We can also represent the main subatomic particles with nuclear symbols. So a proton can be represented like this. The proton has 1 proton, so its atomic number is 1, and its mass number would also be 1 because there aren't any neutrons. And for the symbol, we just use P for proton. The neutron, N for neutron, has 0 protons, but the mass is 1, and so its mass number is 1. And then we have the electron, E, and its mass number is 0, and this is a little strange, but we'll see why. The number of protons is -1. So just kind of put that on hold in your brain for a couple minutes. So let's look at alpha decay. In alpha decay, we have an alpha particle that gets emitted. An alpha particle is composed of 2 protons and 2 neutrons. So this is identical to a helium nucleus. A helium nucleus. 2 protons, 2 neutrons. So here we have an illustration. This nucleus is unstable. So we've represented that by this kind of orange, yellowish glow, like it's, glowing or something. And we see that 2 protons and 2 neutrons are sort of erupting from this, and then they're going to shoot off. And now what's left is a nucleus that's more stable. Of course, this is just an artist's, idea of what's going on here. We can't actually see any of that happening. So the alpha particle can be symbolized as He 42. So 4 is the atomic number, and the number of protons is 2. The alpha particle is not a helium atom. It doesn't have any electrons. But when we're talking about nuclear chemistry, we really don't care very much about the electrons. We're focused on the nucleus. So we refer to it that way. We write nuclear equations to represent nuclear processes. And in a way, these are very similar to molecular chemical equations in that they need to be balanced. But now we're concerned with balancing in a more detailed way. So we're looking at the mass number. So the mass number of everything in the reactant side and the mass numbers of everything in the product side need to match up. And the atomic number of protons, also needs to match up. So here we've got 92 on the left, we have 90 plus 2 on the right. 238 over here, 234 plus 4. We have a parent. The parent is spitting off a nuclear particle, and then it's becoming something else. So we call that the daughter. I don't know why, that's what they call it, the daughter nuclide. So we've got the daughter nuclide, and here we have the alpha particle symbol. So what is very, very different about nuclear chemistry is that the elements are changing into different elements. So I've hammered into you when you're balancing equations and stuff, you can't change the elements. We have to, if there's a helium atom on this side, there has to be a helium atom on this side, right? It's got to all balance. You can't change something into another. In chemical processes, there's always this little footnote that's excluding the nuclear process. So in a nuclear process, the elements change into other elements. So when we look at this product, if this is going to emit an alpha particle, the alpha particle is coming off, and then by doing some very simple math, we can figure out the mass number and the atomic number of the daughter nuclide. And then to identify it, we look for 90 on the periodic table. Because this thing has 90 protons, that means it's thorium. And so we put the symbol in there. So let's write the nuclear equation for the alpha decay of polonium-216. These are a lot of elements that you probably don't know the names of them. Like if I asked you, what's the name of this element with the symbol PO, I would not expect you to be able to tell me that. But you can do all these problems without knowing that it's polonium. So to write this equation, we're going to start by writing the nuclear symbol for that parent nuclide. So we have PO for polonium. The number after the symbol is the mass number. So 216 is the superscript on the left, and we find the mass, the atomic number, by looking at the periodic table. Finding PO, it's element number 84. So 84. That is going to react, not with anything else, but it's just going to spontaneously emit an alpha particle. Now, it's not convenient for writing out the products, but generally the daughter nuclide symbol is given first and then the alpha particle. So I'm just going to leave some space there, and then I'm going to write plus He42. Because this is the alpha particle. And that is something you should memorize. Alpha particle is a helium nucleus. So now what we're going to do is we're going to just do some simple math. We've got a 216 here. We're going to have a mass number here, this mass number plus 4 has to equal 216. Right, so 212. And we have 84 for the atomic number. Over here we have 2. So this atomic number must be 82. It's probably the simplest math you'll have to do all day. Then we have to figure out which element is this. Again, we go back to the periodic table. We look for element number 82. That's lead. So we write the symbol for lead, Pb. Not too bad, right? You got to remember what the alpha particle is. And then if you just follow this very simple process, there you go. Any questions? So, some characteristics of alpha decay. We often use a sort of a vehicle analogy to help us remember some of the characteristics of the 3 major types of radioactivity. So we think of alpha radiation as being an 18-wheeler truck, so semi-truck. It is the most massive particle, the largest particle that's emitted, so semi-trucks are big, right? It has the highest ionizing power, but the lowest penetrating power. So ionizing power, as the name suggests, is the ability to ionize other atoms. So to knock electrons off, and this can cause a lot of damage to biological organisms because you've got atoms in your cells, and now this radiation comes in and turns them into ions, and ions do not react in the same way as atoms do. And so it messes up all kinds of things. They can kill cells or can cause them to reproduce abnormally. Sometimes that becomes cancer. So ionizing power. So ionizing power in the traffic analogy is like smashing into things, right? So the semi-truck smashes into a brick wall, the brick wall goes to smithereens. Penetrating power, I believe that's on this slide, yes, is the ability of radiation to penetrate matter, to go through matter. And in the vehicle analogy, this is like ability to get through a traffic jam. So if you're driving a big semi-truck and you're in downtown New York City and there's just traffic everywhere, you're going to have a very hard time getting through, right? You could smash into something very nicely, but you can't wiggle through this traffic jam because you're too big. Alpha decay has the lowest penetrating power of the different types of radiation. So you can stop alpha particles with even a sheet of paper, your clothing. A barrier of, an air gap will will stop alpha radiation. So it's very easy to stop it. But if it does hit cells, it will ionize things. So alpha radiation is relatively safe as long as it stays outside your body. So it can't get through your shirt. But if you ingest it, if you swallow it or you inhale it and get it into your lungs or it gets into your bloodstream, then it can be very, very dangerous because it will ionize all kinds of things. Any questions about alpha decay? On to beta decay. So here we have the unstable nucleus emitting an electron. Does that seem weird? The nucleus is emitting an electron. Okay, so in an atom, where are the electrons located? Outside the nucleus, right? Are there any electrons in the nucleus? No. So how can we spit out an electron? So it turns out that these subatomic particles can also change into other things. So a neutron can split apart into a proton and an electron.
What?
Right? Blow your mind. What the heck? Yeah. So in beta decay, we have a neutron turning into a proton. What's left of the neutron is an electron, and obviously that does not belong in the nucleus, and so that gets shot out. So here we're looking at carbon-14. When it undergoes beta decay, it turns into nitrogen-14. The mass number doesn't change, but the number of protons changes, because we've taken a neutron and changed it into a proton. And what gets spit out is the electron. And this is why the atomic number in the electron symbol is -1. Because we need this to work out a neutron turning into a proton plus an electron, and 1 plus minus 1 is 0, and so that works out. So here's another example of radium undergoing beta decay. There's the electron. The mass number doesn't change, but the atomic number goes up by 1. So radium turns into actinium. So beta radiation is like a 4-door sedan, less massive than alpha particles, and so they have less ionizing power. So you hit something with a 4-door sedan, you're not going to do as much damage as if you hit it with a semi-truck, right? So they have lower ionizing power, but they have higher penetrating power than the alpha particles. So a 4-door sedan is going to be able to maneuver through heavy traffic more easily than a semi-truck. Beta particles can get through matter more effectively than alpha particles can. So it could be stopped with a sheet of metal, a thick piece of wood, but your shirt or a piece of paper isn't going to stop it. It's just going to go straight through. So beta decay is more dangerous outside your body because it can easily get into your body. But it does less damage once it gets in because it doesn't have as much ionizing power as alpha decay. Gamma ray emission, here what's coming out is not a particle at all. It's just some energy, electromagnetic radiation. So high energy photons. Gamma radiation is at the high energy end of the electromagnetic spectrum. So gamma rays being energy, there's no charge, there's no mass. So when you have gamma emission, the mass number and the atomic number of the element don't change. So the symbol for the gamma ray is the gamma symbol 0 and 0 because it doesn't change either of these. Typically gamma rays will be emitted along with alpha or beta particles, but they could be emitted just by themselves. So gamma rays are the motorbikes of radioactivity. So lowest ionizing power, but highest penetrating power. So, smash into a brick wall with a motorcycle, it's not going to do nearly as much damage, right? But if you're in a traffic jam, you could get through on a motorbike because, even if traffic is complete standstill, you can go between the cars or up on the sidewalk. Gamma rays can get through lots of things. So in order to stop it, it takes several inches of solid lead to stop it, or very thick slabs of concrete. So this stuff just goes through almost everything. But when it hits you, it doesn't have the damaging power that alpha and beta radiation have. It still has ionizing power, but not as much. So here we have an example of a nuclear equation. Here we've got uranium-238. This is undergoing alpha decay and gamma ray emission. So this gamma ray emission often happens along with something else. Next one is positron emission. A positron is the antiparticle of the electron. So in science fiction, they like to talk about matter and antimatter, right? There actually is such a thing. A positron is an anti-electron. It has the same mass, but the opposite charge. And it's not only just an electron with an opposite charge. If a positron and an electron collide, they annihilate each other. They're gone. That's what? Right? Yeah, there's nothing left. There's no electron there. It doesn't turn into a proton or something. They annihilate each other. Poof, they're gone. Energy is released in that in the form of gamma rays. So electrons have matter, have mass, right? Very, very tiny, but they do have mass. One of my favorite t-shirts is, electrons have mass? I didn't know they were Catholic. So positrons also have mass. And so here you have these two, I'll give you very tiny particles, but they do have mass, collide with each other, and now there's no mass. What happened to the mass? Well, the mass turned into energy. Yeah?
So is a gamma ray like a wave?
A gamma ray is electromagnetic radiation. It is the same thing as visible light, but much shorter wavelength, much higher energy. It's the same thing as radio waves. Yeah. So all of those things, just different wavelengths, different energies. They all travel at the same speed. What speed is that? The speed of light. That's one of the favorite trick questions on one of the 1A labs. You know, order these different types of electromagnetic radiation in order of increasing speed. Yeah, you remember that one. They all travel at the speed of light. Okay. So in positron emission, you get a proton being converted into a neutron and spitting out this positron. So this is one I just try not to think about too hard. You just kind of memorize this. So the proton turns into a neutron, and then what do we need to do with the numbers to make the math work out? Well, this needs to be a 0, and this needs to be a 1. We'll often put positive here because we don't want this to be mistaken for an electron. So this is +1 E. This is the anti-electron. So here we have an equation showing positron emission. So there's the positron. The atomic number is going down by 1. The mass number is staying the same. So positrons being anti-electrons and beta particles being electrons, positrons are similar to beta particles in terms of ionizing and penetrating power. Here we have an illustration of a carbon-10 nucleus undergoing positron emission, turning into a boron-10 nucleus. Electron capture is a little different because we don't have something being emitted, we have something being absorbed. So this is when an electron gets captured into the nucleus. Oh, this is kind of weird, right? It's an electron from one of the inner orbitals of the electron cloud. So it's one of the atom's own electrons. It's not something that we're shooting at it. It's something from its own electron cloud. Gets absorbed into the nucleus, and the net effect of that is that we've changed a proton into a neutron. So this is the opposite of the equation we looked at when we were looking at beta emission. Beta emission was a neutron turning into a proton plus an electron. Well, this is sort of going the opposite. We've got a proton from the nucleus and an electron coming in from the cloud, and those combine to form a neutron. So when this happens, we see that the atomic number decreases by 1. We're adding, though, the electron to get the new element, electron capture. Any questions? So this is a figure from your textbook that summarizes all of these things. Looking at changes in the nucleus, atomic numbers, mass numbers. It gives examples. The symbols here are important for the different particles. We didn't talk about penetrating power or anything with the electron capture because it's not spitting something out. It's taking something in. So we should be able to write nuclear equations for different types of radioactive processes. So, question here is write 3 nuclear equations to represent the nuclear decay sequence that begins with the alpha decay of uranium-235, followed by a beta decay, and then another alpha decay. So we'll start with the uranium. Uranium-235 is the mass number. We get the atomic number from the periodic table. Uranium, where'd you go? 92. These radioactive ones are all at the bottom, so that can help you find them faster. So beta decay. So we draw an arrow, and I'm going to leave a space here because I need to put the element in there, the daughter. What's the symbol for beta decay? I'm sorry. Yes, I was looking at this followed by. Yes, alpha decay first. What's the alpha particle? Helium nucleus. So He 4 2. Then we're going to identify the daughter nuclide with some simple math. We need 4 plus something to equal 235. So 231. And then for the atomic number, something plus 2 to equal 92. That's 90. There is no shame in using your calculator to do that. Because sometimes, especially when you're taking an exam, 5 minus 1, not a simple thing. Okay, 90. TH. That's thorium, but we don't need to know that it's thorium. We can just write it. So that's the first reaction. Then it says, followed by a beta decay of the daughter nuclide. So we're going to take this daughter nuclide and see what happens when it decays. So there's our thorium. Now we're going to do beta decay. And what's the symbol for the beta particle? That's the electron. So the mass number is easy. It doesn't change. The atomic number, something minus 1 equals 90. So this must be 91. The atomic number went up. So 91 PA. And right now I can't remember the name of that. I think it's protactinium, but I'm not sure. But there's the equation. Any questions? And this is then another alpha decay. So we're going to take this daughter and do alpha decay again. So this is going to give us something plus the helium nucleus. So what's the mass number? 227. And the atomic number? 89. So 89 is a C, actinium. Any questions? The hardest part is just remembering the symbols of the different particles. Write the nuclear equation for the positron emission of sodium-22. So sodium-22, 22 is the mass number. Look on the periodic table to find the atomic number. As you're doing problems like this, try to get the positron symbol from memory first. Don't just go look it up. Try to remember what it is, and then check yourself. So what's a positron? It's the anti-electron. So the symbol is like the electron, except instead of -1, it's +1. So then our mass number is the same, and the atomic number goes down to 10, and that's neon. So sodium turns into neon. It's very strange. Okay, electron capture in krypton 76. So krypton 76, we need the atomic number 36. Electron capture. So we're adding an electron. So the electron has 0 mass, and it's -1. That -1 is not its charge, but it happens to be the same as the charge, so we could remember it that way. There's no harm in that. So 76 plus 0 is 76, and 36 minus 1 is 35. So this is turned into what, bromine? Yeah. Any questions?